everyone, again welcome to Physical Geology 1A at West Valley College, and I am your professor Farida Baksanusa. Today we are going to study about intrusive igneous rocks. We'll explore the fascinating world of intrusive igneous rocks, those that crystallize from magma deep within the earth. By the end of this session, you will understand what these rocks are, how they form, how we classify them, and why they matter. So let's begin. What is a rock? And let's start with the basics. A rock is a consolidated mixture of minerals. I always tell my students, now after you're taking a geology lecture, you should know you cannot call a mineral a rock, because a mineral is not a rock. A rock is a consolidation of minerals. It's an aggregate of minerals. Okay, so you should know the difference between the two. So a rock is a consolidated mixture of minerals. This means it's hard, strong, and usually contains more than one mineral, though not always. For example, limestone is primarily just calcite. Most rocks, however, are composed of several different minerals. Rocks can also include things like fossils or organic matter. Think coal or some mudstones. Okay. Now, rocks are grouped into three main categories. So, our first type of rock is igneous rocks. Okay, so these are some of the rocks that I have formed from cooling and crystallization of magma. So, you have your basalt, if you go to Hawaii, and those are igneous rocks. Then if you go to Yosemite, that's a granite, and it's an intrusive igneous rock. So that's my granite. You have basalt. That's obsidian. You have basalt. You have a little volcanic rock here. So you have igneous rocks. Then sedimentary rocks. Okay, so you have little sedimentary beds. You'll see a lot during your lab. And they are formed from weathered fragments or minerals precipitating out of water. So classic example, you have your sandstones, you have your breccia, you have conglomerate, you have shale with a lot of fossils. So sedimentary rocks, since it's a very slow process formed over a long period of time, you see a lot of fossils in them too. These are your sedimentary rocks. And then your third one is metamorphic rock. Metamorphic is just like a caterpillar morphs to a butterfly. Your existing igneous and sedimentary rocks undergo high temperature pressure changes, exist, and they get altered even by chemical action. They change to a new rock, and that is your metamorphic, which is this. So you will see very similar traits like the parent rock. So say it is from a shale, which is your sedimentary rock. It will look like a shale, but it's called slate. Okay, so the chemical composition is changed. This is a gneiss, Gneiss. Okay, so that's your metamorphic rock. You have your slate here, and you have peridotite. So I always say my students, peridotite is a state, California state rock. So igneous, metamorphic, sedimentary. Second most important is your rock cycle. The Earth's crust is in constant motion. Rocks are continually forming, breaking apart, and reforming. Okay, this interconnected set of processes is called the rock cycle, and I'm going to put in a beautiful rock cycle diagram. Makes sense. How igneous is converted to sedimentary, how they weather, how then sedimentary rock undergoes heat and pressure temperature changes to form metamorphic rock, and how then magma melts and forms igneous rocks. The rock cycle is driven by Earth's internal heat, creating mantle movement, volcanoes, etc. The hydrological cycle, weathering, river transport powered by the sun. Unlike the moon, which has a dead rock cycle due to a cold core and no water, the Earth cycle is still alive. You can start the cycle anywhere, but let's begin with the magma, molten rock with temperatures between about 800 to 1300 degrees Celsius. Magma can cool slowly underground, forming intrusive igneous rocks, or erupt and cool quickly on the surface, forming extrusive or volcanic igneous rock. Intrusive igneous rocks are also called plutonic igneous rock. Classic example, your Half Dome and El Capitan from Yosemite. Intrusive versus extrusive igneous rocks. Or intrusive, which is plutonic rocks, are formed from magma cooling within the crust over thousands to millions of years, typically between hundreds of meters to tens of kilometers deep. Then you have your extrusive igneous rocks, volcanic rocks, that's magma that reaches the surface and cools. Think about Hawaii basalt, you're walking on the basalt, that's extrusive igneous rock. Intrusive rocks, once formed, have to be uplifted and exposed by erosion for us to see them at the surface. Classic example, Half Dome and El Capitan. The magma story, formation and composition. What is magma? Mostly just 8 elements, okay? So it's made up of almost half of oxygen, silicon, aluminium, iron, calcium, sodium, magnesium, potassium. Magma composition depends on the source rock and how it melted. Mantle magma is more iron, magnesium, calcium. Crystal magma is more aluminium, sodium, potassium. Now, sorry about the baby knocking. This is where I shoot my videos. This is the office that I am, and I have a 2-year-old knocking on the door. Sorry about that. Magma also carries volatile elements like hydrogen, carbon, and sulfur. These become gases. Now, partial melting. How magma forms rocks seldom melt at all at once. Think of a candle made of wax, plastic, glass, and aluminium. At 50 degrees Celsius, wax alone melts. Raise the heat, plastic melts, but glass and aluminium stay solid. This is partial melting, and the melt created is different in composition from the original, just like in nature. How does this happen in real rocks? Decompression melting. Rocks rises, pressure decreases, melting occurs. Melted plumes, mid-ocean ridges. Flux melting. Now, water from subducting plates lowers melt temperature, typically at subduction zones. Most partial melting yields magmas richer in silica than their source rocks. Now, crystallization of magma, a very important reaction series. It's called the Bowen's reaction series. Important, see the diagram in your textbook. I'll put one here too. As magma cools, minerals crystallize in a well-defined sequence. This process is called the Bowen's reaction series, named for Canadian petrologist Norman Bowen. Here's how it works. At high temperatures, the first crystals to form are olivine and calcium-rich plagioclase. As temperature drops, olivine may react to form pyroxene, then amphibole, then biotite mica. Sodium-rich plagioclase forms next. The last minerals to crystallize at the lowest temperature are potassium feldspar and quartz. Now, if you start with mafic magma, you get mostly early forming minerals, felsic magma, more late forming minerals. So, felsic magma. So, if you start with mafic magma, you get mostly early forming minerals. Those are the ones rich in magnesium and pyroxene, and then you have felsic magma, which has more silica. So, those are the late forming minerals. Okay. Magma evolution, fractional crystallization. Since early form mafic dense minerals can settle out at the bottom of the magma chamber, fractional crystallization makes the remaining magma at the top more silica rich, which is felsic. Crystals may remelt if they sink to the hotter depths, adding to the diversity of rock types produced. Now, based on the heating, the temperature, where it's formed, all of that which we studied in the Bowen's reaction series, we can determine the textures of intrusive igneous rocks. Crystal size depends on cooling rate. So slowly cooling, deep underground, you have large visible crystals. It's called pheneritic texture. Two-stage cooling. Some large crystals in a finer matrix, porphyritic texture. This happens if magma starts cooling slowly, but then is transported or erupts, so the rest freezes quickly. So you have a combination. Okay, slow magma then erupts and then it freezes. Crystals in intrusive rocks are often large enough to be easily seen. Okay, so when you see a granite rock, you will see its crystals really well. You'll be able to see the plagioclase, you'll be able to see the quartz. Whereas if you see a basalt, you'll just see black. It must be very difficult to find the crystals. Crystals in intrusive rocks are, like I said, very easy to see. Sometimes they're several centimeters across, especially if there is a lot of water in the magma. Now we spoke about the classification. We can call it felsic, mafic, but there are two more words. They're always more in science. Felsic, intermediate, mafic, ultramafic. So based on mineralogy and chemistry, mainly silica and ferromagnesium content. Okay, so let's talk about some minerals. I show you a chart too. We're talking about the color, what are the key minerals, and how much silica do they have. Okay, so felsic, light minerals, light color minerals have 65 to 75% of silica, and quartz, K feldspar, you have the sodium plagioclase. Okay, and your example is classic is granite. Okay, so granite is your example. Then you have your intermediate magma. So intermediate magma will have will be gray in color. It'll be kind of felsic, but intermediate, a little darker. Like 55 to 65% of silica and amphibole, CaNa plagioclase. And your classic example is your diorite. Okay, I think I might have a diorite like this. this. So it's intermediate. It's got white and it's got a little black too. Okay. Let's go to mafic. So it's dark in color. And so these will be your mafic rocks. 45 to 55% of silica. And you have your pyroxene, Ca plagioclase, olivine. An example would be gabbro. Okay. Now let's talk about ultramafic. So ultramafic is very less silica and very dark. It's less than 45% silica, and your example would be, it has olivine, pyroxene, and your classic example is peridotite. Okay. Another important note is felsic rocks have 1 to 20% ferromagnesium dark minerals. Intermediate have 20 to 50%. Mafic has 50+%. And non-ferromagnesium minerals include quartz and feldspars, ferromagnesium, biotite, amphibole, pyroxene, and olivine. Now, shapes of intrusive igneous bodies. Plutons. Not all intrusive rocks are created equal. Pluton, any large body of intrusive igneous rock. Batholith, huge irregular plutonic bodies, okay, like Coast Range batholith, Vancouver to Alaska batholith. Stock, smaller version of a batholith. A sill, a sheet-like intrusion parallel to the layers. So these are the layers and you have an intrusion, that's your sill. Whereas a dike is the opposite, it's perpendicular. It kind of cuts through all the different layers of rocks. A laccolith, a blister-shaped sill that pushes over overlying rocks. Pipe, cylindrical feeder of magma, often to volcanoes. Sometimes pieces of country rock break off and become trapped. These are called xenoliths. Interactions with surrounding rocks, chilled margins. So example, for where hot magma contacts much cooler country rock, the magma cools rapidly at the contact, forming a chilled margin, fine grained on the edges and coarser, because coarser ones, remember, they got more time to cool, so your crystals can be seen, and because there was chilled margins, didn't get much time to cool, they're finer grains at the edges. Now, why do intrusive rocks matter? We did this whole chapter on it. Key to understanding Earth's interior and tectonic processes, right? If we didn't know that granite was an intrusive igneous rock, how would we know that there was weathering, there was plate movement? To study geology, basically, study the past history. Major sources of important resources, metals, gemstones, industrial minerals, form the roots of mountain ranges and influence landscapes. It forms clues to geological pasts, right? Ancient batholiths now exposed record tectonic events millions of years old. So now let's summarize. Intrusive igneous rocks form deep in the crust from slowly cooled magma. Their textures and minerals are clues to their origin and history. The Bowen reaction series helps us understand mineral formation and magma evolution. The shapes and sizes of plutonic bodies from dikes to batholiths reflect the complex dynamics of magma movement and emplacement. Studying these rocks lets us peer into Earth's deep interior and unravel its history. Thank you for joining me for this lecture. Make sure you answer your questions. If you have any questions, feel free to email me on Canvas. And remember, stay curious. Keep exploring the deep time beneath your feet. And the next time you see granite, remember, you're looking at crystallized remains of a primeval magma chamber deep within the earth. Right now that you've taken geology with me, you would know that. You can tell your friends who've not taken geology. I'll see you in the next lecture, and if you have any questions, message me, email me. Thank you so much.